Hello.
Hello. How are you?
Good to see your face.
Nice. Just to confirm that whether all of you are ready to continue or not.
Yeah.
Great. Then I will share my screen.
Okay.
Can you see my screen?
We do see. Yeah, I can see.
Okay. Great. So today I will say a few words about sequential testing, which is a family of hypothesis testing or usually A/B testing. But nowadays it's getting more popularity than other classical A/B testing approach. So a few words about how the sequential testing is working and some of the algorithms behind this sequential testing. The left, the detail behind the testing procedure or the mathematics to you to read more, as all the supporting materials are already included with the doc which is created for this week challenge. So as the name indicates, the sequential testing is so it allows us to just test our significant testing for each of those observations that we are gaining or that we are collecting from our data source than waiting for fixed size sample size that the current classical A/B testing approach are looking for. So we know that in classical A/B testing, to get lower error, we require the larger sample size, but the difficulty behind is how to decide that large sample size is the question still. A number of statisticians are now researching in this area still now, and we are expecting otherwise the smaller difference between the two variants that we are measuring. Otherwise, when we talk about A/B testing, we have A and the B, two variants, and we have the null hypothesis, the hypothesis that we are going to justify in our statistical procedure, and we have alternative hypothesis that which is usually in our data scenario, if we take, we have the exposed group and the control group. Control group is our base data, and the exposed group is the one that we are expecting the change. So our alternative hypothesis will be the getting better change in the exposed group. That is, we have two data group, so we are expecting, let's say, B is greater than A. So that is something that we want to prove. But we have also null hypothesis, which is saying the two groups are similar, or maybe there's no difference between the two data groups. So that's the idea behind testing, the hypothesis testing. But in sequential testing, so the procedure is similar with the classical testing approach that we are using. The only difference is, instead of looking for the maximum sample size that we initially defined, we are with this objective. In sequential testing, we come up with the three decision, that is either hypothesis, or either keeping our null hypothesis and stop the testing, that is accepting the null hypothesis. But don't forget that accepting a null hypothesis means control group. It's not to say control group is better than exposed group. Statistical process, but just we are keeping our initial hypothesis true. That is, there is no difference between the two variants. And if we can't able to reach with the existing data or with the existing observation, the test hypothesis will give us simply continuous state. So we are looking for additional data to come up with decision. So with this, we get at least 3 advantages. One is the sequential testing allow us to get early decision, so that we don't wait for the large size data. And even with this small size data decision, it still keep the it does not increase the possibility of false result. So we finish the test, we finish the experiment with small data size, but keeping the false rate as usual as a classical A/B testing approach. So the big thing here is, unlike the classical approach, where the significance is only checked after all samples have been collected in the traditional way of working A/B testing, but here, as I said earlier, for every new sample, we apply the testing, we get the result, and it also guarantees us both the type 1 type 2 error as of that the fixed size classical A/B testing give us. So in industry, commonly these two algorithms are used in sequential testing. One is the Ivan-Miller sequential testing algorithm. You will get this notebook, so that it's under the folder. Maybe Jane can share this with you after the discussion. So one is the
I will share. I will share. Do you already put it in the folder?
Yeah, it's under notebook folder.
Okay, so but is in Tuesday folder for learners? No, I don't think so. But will you share?
Okay,
I think
so
by the end, you will share the link with me, and I will share with them. I will put in the right folder.
exactly.
Yeah. Okay.
It's under.
Okay.
Yeah.
Yeah, just share with me later when you finish your presentation.
Okay. So this Ivan-Miller sequential testing approach is very simple approach. Initially, we are expected to set the sample size. So I have just associated the link. It's a kind of similar to the classical A/B testing approach when deciding the sample size, but Ivan-Miller himself just created the demo page that allow you to define the initial sample size if you want to use the simple sequential A/B testing algorithm. You can go through this link, and we need to arbitrarily assign the initial probability. I mean, that is the initial success rate, 50% probability for each of the exposed and the control group. Then we need to, we have two data group. One is the exposed group that we call the treatment one. Another is the control group. So our aim is, if it is one-sided test, our aim is to prove that there is no difference between the two. If our aim is working in two-sided tests, we need to check for whether the exposed group is greater than control group, or again the control group is greater than for the exposed group. But for the one-sided test, we track all the success values coming from the exposed group and assign it as a T. Similarly, we track the control group success data, which is just one is the yes value in our case, in our data case. Then the stopping rule is very simple in this scenario. So we just get the difference between the success values we collected from treatment group and control group, and apply 2 over square root of the sample size we defined. So if this difference is it reaches or less than this 2 over square root of n, we just declare that exposed is the winner hypothesis. And if the sum of this, the success values reaches to the sample size, we just stop the test to say that there is no winner, which is accepting the null value. So the two-sided test is also the same. The only thing in the ending, the stopping procedure, we just add 2.25 than we use 2.25 than 2, and it also allow us to get both either of the two, either the treatment or control is the winner, because the test by itself is two-sided test, or sometimes we call it as two-tailed test. But the main thing here is this approach ignore to consider number of failure in both of each group, which is we don't bother the negative response rate. Plus, it's not known. It's initially no. It's not known to stop, when to stop the experiment, and if we hit the threshold without having the statistically provable result, that means if we can't able to reject the null hypothesis or accept the null hypothesis, and if our final observation reach to the n size, which we defined, so we have no way to continue the experiment. So this thing is still not fixed in this algorithm. So because of these two drawback, people are looking for some custom algo in this area. So you can read more from the link that I have associated with the Ivan Miller simple sequential AB testing and the sample size finder link here. So because of these two limitations, nowadays the sophisticated tools such as Statistical and other related engines are looking for another algorithm, which is now popularly used, that we ourselves in Abebaw we are using this sequential probability ratio testing algorithm. It has 3 variants. One is the popular Wallis sequential probability ratio test, another is conditional sequential probability ratio test, and sequential generalized likelihood ratio test. All of the 3 algorithms use the likelihood ratio statistics. So we will get the detailed mathematics behind the 3 algorithms in the link. And if you get confused, just to understand some of the basic concept, you can write in the channel and we will go through it. But if you choose to work with Wallis sequential probability ratio test, it's very simple to implement. But the problem is it ignores the tied observation, which is how the control and experiment the group are related. So this ingredient is the basic thing that we need from the test. But this test it changes the process of checking to the single proportion test, and the algorithm itself expects the sequence of zeros and the ones in a single data array. But in current scenario, if you look at your data, you have 2 data groups, the exposed and the control group. So if you want to work on this Wallis sequential probability ratio test, you need to come up with another technique that change your 2 group data into 1 data series, but keeping the information from both sides, from both the control group and exposed group. So there is one algorithm that, if I remember, it's it's called as the interleaving, which is popularly used in the web, especially when web algorithms are ranked, whether which ranking algorithm is better, give the better response. So if you read in that area how the ranking algorithms are interleaved together, when the search engine select the best ranking algorithm, you will get ideas from there, and you can apply here to come up with the tied observation between the two exposed control group. But I just provide one algorithm in this notebook, which easily you can understand the concept behind the code, which use the conditional sequential probability ratio test, not the wireless approach. So I will leave this part open to you. Read the detail behind this conditional sequential probability ratio test and sequential generalized likelihood ratio test. But the implementation which is included in this notebook is the conditional sequential probability ratio test. You will get the R version and Python version for wireless implementation, but R version for the conditional sequential implementation. And here for the generalized likelihood ratio test, the link itself is implemented using node.js file, which is the JavaScript version. So you can read and understand and use for your challenge. So the idea.
Okay, so I think.
Okay.
Yeah, so both they are going to have the code, R code and Python code for sequential hypothesis testing. Okay, feel free share with me the link for all the notebook, and I will put it in the today folder. And guys, I know that I didn't introduce you to R because of the amount of time we have. We wanted to focus on only one programming language, but it's no problem. I think if you are going for, if you manage to go for the R notebook and you don't understand anything, just tag me directly or contact me. I will be here to help you as well. No problem with R. Yeah. So Abebaw, is that all for the session?
Yeah. A couple of minutes, then I will complete.
Okay, sure.
So let me say a few things about how the sequential probability ratio in general works for all the three algorithms. So initially, we need to set the general statistical parameters like alpha, beta, and odds ratio, the real difference between the two groups. Then we need to calculate the upper and the lower critical values. So because the nature of the testing by itself is sequential, we have the upper and the lower values. Otherwise, because the data group is is enriched incrementally, so we have the values which are incrementing. The log likelihood ratio by itself is also incrementing. So we need to calculate this upper and lower critical values. And this is the formula to find out the decision boundaries. You will get the detailed mathematics from there. It's very simple, but for each of the observation, so you get the entry for control and exposed group first, then calculate the test statistics, which is likelihood ratio. Then you also expect to calculate the upper and the lower limit values for the exposed group, which is the one you want to assure, because our aim is otherwise to get the better conversion in exposed group, the new group that we are expecting, and apply the stopping rule, which is simply the log likelihood ratio value that you have calculated at the current state. And if that is greater than or is equals to the b value, which is log 1 over beta, 1 minus beta over alpha. So you accept your alternative hypothesis, which is rejecting the null hypothesis. And if the value is less than or is equals to or below the lower critical value, you are accepting your null hypothesis, which is there is no difference between the two data group. And if it lies between A and the B value, otherwise your value will be in the continuous state. So the plot will look like this. So you have two decision boundaries. One is for the null hypothesis, and the other is for the alternative hypothesis. So until it hits any of the line, it is the continuous state. That is, you are looking for more data to apply the test. If it hit any of the line, means you are rejecting the. If it hit the acceptance line, you are accepting your null hypothesis. That is, there is no difference. If it hits the rejection border, you are rejecting the null hypothesis. That is the alternative. I mean, the exposed group has better conversion than the control group. So the two sides is also similar. So I have included few codes here, so you will easily read the data. So let me open this notebook. So this is not structured code. I just included several functions because I want to make it open to you to understand first how each of the function in this paper. This is the original paper, the conditional sequential.
Abebaw, are you sharing your screen or are you presenting? Do you want them to see something visually? Because you are not presenting actually. I don't know if you want to, or it's okay. Is it okay?
Okay. Is that not visible?
No, we can get your screen.
Oh, still no. Sorry, guys. I was thinking.
Yeah, I think it's okay now.
Sorry, really sorry, guys. Is that visible now?
Yeah, it's. I think we see it like the screen, like presentation, but not yet the notebook.
Let me reshare. I can. Is that visible now?
Yeah, I think it's okay. Great.
Okay, great. So under this cell, I just included all the detailed implementation behind the conditional sequential probability ratio test. All the variable names are similar to the variables which are included in the initial maker's paper. So I just keep the reference here. So read this paper first, download it, read this paper, and when you understand the mathematical concept behind this sequential, in the paper, you will get all the variables here, all are implemented. But as you can see easily, this is not Pythonic approach. I just write all the function not in an optimized way, thinking that you will understand this code and refine it in a better way. Because if I raise simple example here we have iteratively, recursively calling a function. So consider that we have 1,000 observation. So we are going to call this call function 1,000 times. In Python, very costly computation is iteratively calling the function. So considering these, just understand how the functions are included here. all the variables are as I say, it's similar to variables which are included in the paper. So you will easily understand how things are implemented here. Then once you get the concept behind, if you want to continue with this conditional probability test, just change this to a bit optimize the code and rewrite it under this sequential test class. I just included some of the class for your challenge. So you need to compute boundaries, you need to have a stopping rule, you need to keep the initialization, the startup variables will be used throughout the class. The plot boundaries. Plot boundaries means you need to plot how the success rate of exposed group is related to the critical limits that you compute. If you when you understand this code behind, the terminologies behind sequential test will be easy for you. Once you get the detail behind, you need to plot the test itself. So if my notebook is open here, let me show you how we compute in our other module.
Okay, leave you to it. Project is tomorrow. Sorry? Project is tomorrow. Oh, today's a Tuesday.
Okay, so I will show you when that. So another thing is transforming your data. From the data, the only comment that you need to yes and no for this sequential testing, the yes and the no column only. The rest features are to be used for your machine learning and another analysis part. So this information help you how to transport the data into the somehow sequentially organized way. So understanding using this concept, you need to transport the data and have data binary data Bernoulli series stream for both exposed and control group. Upload the data summary. Similarly, you are also expected to have the print test result. So this result will be something that you are expected to present to the non-technical person. So understanding the detailed concept behind A/B testing and include all the values here. So this is how you are expected to define the sequential probability test. So you are not forced to use this conditional probability test. You can use any of the algorithms that I have mentioned above, but focus on the drawbacks behind all of them. You have two data groups, but you are expected to have also the tied observation between the two data groups. So if you want to continue with Wald's approach, you need to come up with interleaving issue, how to interleave the two data group without losing information from any of them. If you want to continue with conditional probability test, all the detail is implemented in this set, but it's not in efficient way. You need to rewrite all the function in efficient way and complete this class and function information. So this all, I'm happy if you have any question related to this sequential testing and we can discuss.
Great. Yeah, so guys, I hope you enjoyed the session, the sequential A/B testing session. And if you have any question now to Abebaw, this is the time to ask. Yeah, you can ask in both the chat inbox or directly. You can request to speak, and I will give you the right thing. Then you go. Any question? Is that clear? Is everything clear or not clear at all? So if there is question, then just ask. It seems that everything is clear. I think Abebaw will share with me the notebook with Yabi, and we will put that in today folder so that you can get it and go through. And from there, I think you will get more the things. Yeah, I know it's a lot, so I think you need maybe some time to go through and then check. But once you check and you see that you are not understanding something or you have some question, I think feel free to ask in the Slack, and we will assist about that. Yeah. Yabi, we was okay. Emmanuel have a question. Emmanuel, just go. Unmute and go. Emmanuel, you can ask your question. Yeah. However, there is a question about how should we classify the people who didn't respond in our sample? Like we have both column yes and no, but for both, in case for both we have 0, so that means people are not responding for the. So how did we manage? I think is that. Abebaw, do you have something to say? Maybe he left. Yabi, then?
Yeah. Okay. I think Abebaw probably is disconnected. So
Yeah.
Yeah. Okay. Emmanuel also is. I think so. Your question is clear. So how do you? I mean, this is. It's not classification, right? This is more like there is a time where there is engagement. So there is a time where there's no engagement, but the people have seen it, right? So that's, and that information should help you. Of course, the very first thing is to drop all of them, but that is an information that that you have that will help you who's responding as well. So I don't know what the question means, but you should integrate it in some way that you extract the information out. I'm not sure what other way I'm going to answer. But if you have clarity, I mean, if you have a particular question, you can ask. Like, what do you mean classifying?
Yeah, like I maybe it's like, are we considering those people in the analysis, or are we just removing them? I don't know. Maybe
Okay.
Emmanuel. Yeah.
Emmanuel, yeah. Okay, so I mean, I think you should consider them. Every information you can, the more you remove, the less you have a power, statistical power to say. And I think the simplest, of course, most of the time, what the algorithms that you have probably will just know if something is 1 or not, if someone responds or not. But I would say just think about and discuss how you can incorporate them, because that's an information. Just that's the only thing I can say. In some way, try to always, I mean, I intentionally left them because that is an information that you will have when it comes to rates. You know, when you are computing the rate parameter, so I'm just saying it, so the rate parameter depends on how much engagement there is, or how much yes there is with respect to how much engagement. And to know how much engagement, you need to know, I mean, you need to know the numbers, but sometimes you may need also, instead of just the engagement divided by the number of impression. So that's basically just tells you, I mean, in frequency analysis, that basically means this should be your invariant matrix. So they should be equal amount in both cases. Otherwise, something is wrong, right? So it's kind of use it in that kind of information. I think in the best is if you have a particular question in mind, just ask them. But there is a multiple ways in A/B testing that you will use those informations. And very important and first information is that you will use it to compute rate parameters. Is that clear? Or Abebaw, like you can also answer if you are back.
I think it's clear. It's clear enough.
Okay.
All right. Yeah. If there is any other question, just ask.
Yeah. So I think.
Yeah.
Okay. Great. Yeah. I think use always these things as depending on the algorithm changes. So that's why it's kind of like there is no one answer. For some, it's an invariant metric. For another, it is a kind of predictive way. If you are doing machine learning, that kind of tells you that it's a negative result, right? So it kind of tells you a lot of things about who's engaging and stuff like that. So there are multiple ways you will use that information, but always one way to look at it is that, is there information in it? And most of the time that way of thinking will tell you that how can I extract that information such that to make my model or my analysis stronger. That's the usual way I would ask myself. I think it seems it's quite a complicated, probably, I don't know, I haven't been attending, but if you are, if you want to vent, this is a good time as well. It's just if you didn't understand, somehow was too complicated, blah, blah, you were expecting like very clean, nice thing, and then suddenly here you have a very complicated sequential testing, blah, blah. So yeah, it's good to reflect, to be open about your understanding and your not understanding. And it's okay to not understand it. And it's also okay if you really get excited and just you want to try.
So I'll vent a little bit this option, please. Like the way it's going, you have to it's like you have to do the coding first before you can even answer the first question of like the first.
White and core and
Yeah. Okay. I think if
Emmanuel, if you are hearing, it was just so hard to listen, but if you can just want to say it again, just try.
I think he's muted.
Okay.
Yeah, but hope he get some understanding. And if you still have questions, just let's continue on Slack. And yeah, so okay, I'll connect with my. Yeah, we can continue all this in Slack, no problem. Because okay, so I asked Abebaw to share the files in.
I think it's already there. I'm gonna just put it in
okay.
it's
Sure.
there. So
thank you, Yabi. Yeah, thank you.
Thanks everyone.
Okay, so I'm
Cheers.
stopping. Cheers.
You're stopping the record, right?